I welcome Professor Abhishek Dhar from ICTS TFR Bangalore to talk about entropy growth during free expansion in a specific ideal gas.
Okay, so first I would like to thank Pinaki and Arnab for organizing this and for the invitation. It's really nice to be in IMSC after a long time. I mean, I don't know when I was last here, I think maybe around almost 10 years back maybe. Yeah, so I'll be talking about entropy growth during free expansion of an ideal gas. So this work is done with a large number of people and it's still going on. It's various things. So Shubhadeep Chakravarti, who was I think he was at IMSC at some point, but he was a postdoc at ICTS and now he's in Nuremberg. Two of my students, Junaid Bhatt and Saurav Pandey, two colleagues at ICTS, Manas Kulkarni and Anupam Kundu, and Shelley Goldstein and Joel Lebowitz at Rutgers and David Hughes at Princeton. Okay, so some of this is published in these papers and some of it is still being written up. So okay, so the basic question is something everyone has thought about. I mean, we have the microscopic laws of physics are reversible, but why do we see irreversibility in nature, right? So this is the simple demonstration of that. You take a glass of water and then you put a drop of ink somewhere, and then what you observe is, of course, after some time you see this, you see eventually it becomes a homogeneous mixture, and you never see things going the other way around, right? Even though the microscopic laws say that this is of course possible, that it should go from here to here. Okay, so this is something we all have thought about, and in some sense we probably have some understanding. Okay, so the observed macroscopic behavior of physical systems show irreversible behavior. So we know that the second law in some sense provides an arrow of time and quantifies irreversibility through the concept of an entropy function which always increases with time. Okay, so note that entropy is usually defined for an equilibrium system, and what we say when we say entropy increases, it's like you have some system and you release some constant. So initially it was in equilibrium, and after you release the constant it goes to a new equilibrium, and from one equilibrium to the other equilibrium the entropy you can calculate, and the entropy has what you expect is that the entropy should increase. So okay, so this is of course the question that everyone asks. I mean, how do you get irreversibility from reversible microscopic dynamics, which can be either Newton's equations or Schrodinger's equation. Okay, so this is something which Boltzmann had thought about a long time back, more than 100 years back, and what he observed is that this irreversibility is the most important idea is that that you need a large number of degrees of freedom. Okay, so what he said is that the observed irreversibility is the typical macroscopic behavior given appropriate initial conditions that becomes a certainty when the degrees of freedom is large. So I mean, it depends on initial conditions. You start with very initial conditions typically, and then this irreversibility that we observe is the typical behavior. Okay, so there is also atypical behavior is possible, but that becomes rare when the degrees of freedom are large. Okay, so Boltzmann in fact provided a very clear prescription of how one can construct an entropy function for this irreversible dynamic. Okay, and this entropy is defined for a pure microstate. Okay, so this is actually the main idea that I will try to present in the talk, that you can define an entropy function which is defined for a single microstate of a dynamical system. And this entropy function can be defined both in or out of equilibrium. And in equilibrium it is equal to the usual entropy we know, but it can also be defined out of equilibrium. Okay. So this is the main idea, and this has been discussed in a lot in the literature. Some sort of references that I like are, this is a very popular article, Physics Today, by Joel Lebowitz. It's called Boltzmann's Entropy and Time's Arrow. This is a more technical paper which has a lot of the details of the formalism which I'll discuss today. This is something which is an extension of this earlier work to the quantum case, I mean all these other papers. Okay, so in this work that I will present today, basically it's an sort of very explicit, simple pedagogical example to illustrate this Boltzmann's ideas of constructing this entropy function. Okay, so that's the basic idea. So please ask questions at any point. Okay, so this is what the system will look at. It's ideal gas in one dimension. So let's say I have a box which goes from 0 to L, and there are n particles. These are point particles, so I have drawn them as disks. These are really point particles which are completely non-interacting. Okay, so they can go through each other. And the dynamics is just ballistic dynamics. So each particle moves with some constant velocity, and at the ends it can reflect. Okay, but otherwise they just go through each other and they're moving with constant velocity. That's the dynamics. Okay, and the initial condition what we take is that half of this is, let's say, just half of the box is filled with particles, and each particle has a velocity which is chosen from a Maxwell distribution. Okay, so it's in thermal equilibrium but on one half of the box, and then what we do is we remove this wall, and so that's the free expansion setup, right? That's what we usually study in free expansion. Okay, so this is the initial condition. It's in a thermal distribution, but we choose one realization. Okay, so we don't do an average or realization, which also one can do. We just choose one realization from the equilibrium distribution. Okay, and the particles, this I already said. And okay, so now if I ask what do you expect, even though it's a non-interacting system, there's no chaos or anything, what you naively expect is that at long times this system would in some sense equilibrate. At least if you look at the density profile, it reaches a uniform, and that's what you expect, right? It should go to a uniform state. I mean, some things may not relax, like the velocity distribution, because it's non-interacting, it wouldn't change with time. But it started with Maxwell, so it will stay Maxwell all for all times. Okay, so in some sense we expect that it's going to from some macroscopic state, which is this half-filled box, to a uniformly filled box. So there is some irreversibility we expect, and how do we quantify this irreversibility? Okay, so the basic idea of Boltzmann is the following. So there are two descriptions of a system. One is a microscopic and one is a macroscopic description. So the microstate of this system I am talking about, it's n particles, and is described by positions and momenta of all the particles. So this is the microstate, which I'll label by capital X, right? All the positions and momenta. And then the dynamics is given by some Hamiltonian. And then one can talk of macro state, which is a coarse-grained description of the system. Okay, so now when we observe a system, let's say in the gas in the room, we don't observe all the molecules. We might be observing something like maybe what's the number of molecules in even like small boxes in this room, right? That's what we can observe. So it's a coarse-grained description. This is what we are able to observe. Okay, so such a description describes a macro state. Okay, so this is an example. I mean, if I have this box, particles in this box, then if I just ask what is the number of particles in the left half, that's a macro variable. Okay, so this n left is the number of particles in this left half, and that of course is a function of the micro state, right? So this it's a some function of the micro state x. Given the position and momentum of all the particles, I can immediately compute what is the number of particles on the left half. So it's a function of the microstate. Okay, now the idea of Boltzmann is that if I just specify the macro state, which is the number of particles on the left half, then I know immediately that there are a large number of microstates which will give me the same value for the macro state, right? So we just say, let's say gamma m be the number of such microstates, or the volume in 6n dimensional phase space, which corresponds to the same value of the macro state. Okay, then Boltzmann's entropy for this microstate x is just defined as log of this total number of accessible microstates. Okay, so notice that this looks very similar to what we do in equilibrium physics, right? What is the entropy of system described by energy E, we just compute the volume in phase space, which is for which the energy is between E to E plus delta E, and then take log of that, right? But here what we are doing is that we ask that what is the value of the macro state, and then we ask what is the volume in phase space which is which has the same macro state. Okay, and that gives us the entropy. Okay, so what's good is that we can compute entropy for a single microstate. Okay, so just to give an example, I mean, this is, let's say we take a box like this and we partition it into several cells. So this total length is 7, and I divide into 2, 1, 2, 3, 4, 5, 6, 7 cells. Each cell is size 1, and let's say I just put 16 particles, right? So a microstate would be the positions of all the particles, and this is the macrostate where I count the number of particles in each cell. So given a macrostate, of course, I can have large number of configurations, and I can ask how many such microstates are there for a given distribution of particle numbers. Okay, so in this case, if I know the number of particles in each of these cells, then I can count how many different possible arrangements are there which give me the same number, and this we know that it's given by some formula like this. So delta is just the size of each cell, so delta to the power Na is the number of particles in this cell divided by Na factorial, right? This is the usual volume, sort of volume in phase space for a given the choice of macrostate depends on what we are observing. Right, I mean, like you can observe various things. Like in this case, I can choose to observe just the number of particles in each box. I can also choose to observe the number of particles and their momenta in each box. So that's up to what I am observing.
So the Boltzmann entropy would be different.
Would be different, right? Yeah.
And
yeah, right. Yeah.
So is Boltzmann entropy and thermodynamic entropy two different?
Right. Yeah. So for some choice of macro states, what we'll see is that if the system is in equilibrium, then I mean it agrees with the equilibrium definition, right? I mean, so yeah. So this, I mean, if I just look at n, of course, it won't give me the equilibrium distribution, but because I'm ignoring momentum variables. But if I mean, if my like I may not be able to look at momentum, right? So if I'm just observing like positions, then this is a good description. Okay, so this is the usual counting of number of states corresponding to a given configuration of number of particles, and then if I compute the entropy using this Boltzmann's prescription, then I get some formula like this. So finally it's rho A log rho A. So this is the density of particles in a cell, in the 8th cell, and times log rho A, and I just sum over all the cells. Okay, so this is rho log x dx. I mean, this is the kind of formula that you will remember is the entropy associated with a particular density profile of any microscopic system. Okay, so now so then the basic idea of irreversibility is the following, that let's say this is the entire phase space. Now this entire phase space for a given macro state, value of the macro state will correspond to some volume in this phase space, right? That's what I just and taking the log of that gives me the entropy. So now the entire phase space can be partitioned into parts, each of which correspond to some value of the macro state. Okay, and the equilibrium macro state is one which has actually extremely large volume. It occupies almost the entire phase space. Okay, so in a typical non-equilibrium setup, what happens is that one starts from some from extremely low volume region of phase space. So low volume means if I look at the number of configurations, microscopic configurations for all the particles in this room being in 1/2, right? That's a very unlikely configuration, so it will occupy a very small volume in this entire phase space. Okay, so my initial condition will belong to some very small part of this phase space, and then it's evolving. As it evolves, it's basically going to volumes of larger, it's going to cells which have larger volume in this phase space. Okay, and eventually it goes to the equilibrium cell which has the largest volume. Okay, so that's the rough idea of why we observe irreversibility. Okay, so again, just to summarize, like how one can associate an entropy for an individual microstate, just or an individual wave function for quantum systems. So this is the microstate, and what we say is that our observables are coarse-grained variables, and they are, of course, given this microstate, we can find what is the value of this coarse-grained variable, right? So given the microstate, we can immediately say what is the number of particles in each cell, which is our macro observable. Then what we do is just count the number of microstates corresponding to this value of the macrostate, and so this is this gamma, and then take log of that. That gives us the entropy of the microstate. Okay, so what's most important to observe is that we have entropy for a single microstate as opposed to an ensemble, which is what usually we are used to. Okay, so now like Jitendra asked, I mean, there are many choices possible for the macrostates. So we'll discuss two sort of very natural choices of macrostates in the context of an ideal gas. Okay, so the two macro variables that I'll discuss are, so one is just the empirical single particle distribution, which is this object. So basically you just ask, I have an n particle system with 2n degrees of freedom, but I just ask, like, in a how many particles are there which are located in some cell around xv in single particle space. Okay, okay, so this is, of course, one is familiar with this. This is what arises in, for example, Boltzmann's H theorem and so on. And the other set of macro variables that we'll look at are the usual hydrodynamic fields that are described that are used to describe a fluid, for example. Okay, so for example, the air in this room, the usual description in fluid dynamics is in terms of the density, the momentum field, and the energy field, right? So, so we just take small cells in this room and ask what is the total number of particles in this, what is the total number of, what is the total amount of momentum, and what is the total energy in this cell, and we do it for all the cells in this room, and that is our coarse-grained description. Okay, it's clear that this is a coarse-grained description because there will be a large number of microscopic states which give me the same values for these fields. Okay, so these are the two coarse-grained descriptions of our microscopic system that we will discuss. Okay, so let me first discuss the this first choice, the single particle empirical distribution. Okay, so again, what we do is we have a single particle phase space where this is position and velocity, and we divide it into grids, into small cells with delta x in this direction and delta v in this direction, and we so given a microstate, we can just ask each particle will have a position and velocity that will be a point in this grid, right? So we put all the so we just see where all the particles lie in this phase space, and then we just count how many particles are there in each grid. Okay, so let's say n alpha is the number of particles in the alphath cell, and we then compute this function f alpha, which is just the fraction of particles in each cell, and then from the then we just do this counting. We ask how many realizations are there which have the same number of particles, and this using the same argument that I just gave to get this rho log rho. In this case, we'll get an entropy which looks like this. Okay, so given a microstate, I can immediately find what are these values of F alpha for the distribution of number of particles in each of these cells, and then I can compute the entropy. Okay, so note that this is for a single realization. I'm not doing any ensemble average or anything. Okay, so this is the entropy, and we want to know in this as the system evolves from this in this free expansion scenario. Yeah.
Why is this single particle phase? Because there I can see that multiple particles in the entropy space.
No, so there are n particles which are x1, p1, x2, p2, and so on, x1, xn, pn. But I'm looking at just the single particle phase space distribution, right? Which means in this two-dimensional space, I'm asking how many particles are there. See, if I take any particle, it will fall in some point here, right? Then I just count the number of particles. So, I mean, this is not, the n particle phase space would be 2n dimensional, right? But this is just 2-dimensional. So, in that sense, it's a single particle phase space. But each particle, every particle will be some point in this space. Okay, any other questions? Okay, so right, yeah. So it's clear that for as this gas evolves, I can compute this function at any instant of time, just following one individual trajectory. Okay, so this is again just to remind you what is the initial condition. This is the initial condition. Each particle is chosen from a Maxwell distribution, and they are uniformly distributed in this left half. Okay. Okay, so now if I, so this is the single particle phase space. So initially this is how all the, if I just point to put the coordinate of each particle at some point in this space, and this is like I think maybe 10 to the power 5 or 6 particles chosen from that distribution. Okay, so they all lie on different points, and then I just see how these points evolve in this two-dimensional phase space. Okay, so after some time, what we'll see in this, if you just do this new simulation, you'll see that it develops this kind of structure in this phase space. So it develops these stripes in this direction, and so in space it's kind of uniform, but in the velocity direction you can see that it develops this striped structure. Yeah.
Velocity distribution, which is initially chosen Maxwell.
Yeah. It will stay Maxwell, right? Because these are non-interacting particles. So when particles, they just go through each other. So there's no.
Suppose one particle has velocity 4.
Yeah, it will remain 4 all the time. Right, yeah. So, but it's, yeah, so they are of course distributed from a Maxwell distribution, but each particle maintains its velocity. So we'll also discuss the interacting case where of course they exchange velocities and it's different, but in this case there's no change in the velocity distribution.
Is velocity just coming due to confinement or that's right? These structures are developing just due to the boundaries, or I don't know.
No, so okay, so here I'm showing hard walls. I mean, even if you do it on a ring, you'll see the same structure. So see, basically what happens is, what you can imagine what happens, right? These particles out here, they'll start moving, they are all positive velocities, so they start moving in this direction, these guys move in this direction, right? So this kind of stretches, okay, and then it winds around. Okay, so you just get different windings, and there's no spreading because it's a non-interacting system. Okay, if it is an interacting system, then we'll see later that this will become completely homogeneous. So the fact that the structure is maintained is just because it's non-interacting. Okay, so now given this like distribution of points, we just form our grid, count the number of particles in each cell, and then compute this object. And what we'll do it is we'll use different grid size, this cell sizes. Okay, and see how this entropy growth depends on this cell size. Okay, so what we would like is that this eventually there should be some thermodynamic limit where you take large number of particles and grid size going to 0, and the entropy, this growth function doesn't change with time. Okay, so this is the plot of the entropy growth for different grid sizes. So delta x we keep fixed, while delta v we keep changing, making it smaller. Okay, so it turns out in this model, I mean, as you can see, if you like delta x is the cell, the grid size in this direction, it's kind of homogeneous in this direction, so you don't expect anything to change when you change delta x. Okay, but if you change the grid size delta v, at some point it will start seeing the structure, right? So you expect that things will depend on delta v, because entropy is basically like it has information on the structure. I mean, so question is how much structure can we see in the distribution. Okay, so this is what we see. So this is for some grid size, and then so the entropy starts from at time 0 at some value, which corresponds to the half filled box, and then it increases, and then there are some small oscillations, and it saturates to some value. Okay, so this is for grid size 0.5. This is for a smaller grid size 0.25, and this is 0.1 and 0.05. Okay, so in all cases we see that the entropy eventually it will go to a saturation value, and this change in entropy is exactly log 2, which is what we expect for this free expansion from half volume to full volume. So this change is always log 2, but it just takes longer time if you have a finer grid. Okay. Okay, yeah. So this realization is for 10 to the 7 particles, and okay, so in this plot you can see there are two plots. So the one is the blue thing, and one is the squares. The squares are with just a single realization, and the lines are when you also do some averaging over initial conditions. Okay, so you can do average over initial conditions with I mean always the same macroscopic state, and you see that a single realization and average agree perfectly. Okay, so now you can look, so instead of looking at the entropy, you can also look at this, the actual distribution function, how it evolves in time, and what you see is that at time 0, okay, so this is space and this is momentum and this is f of xv. So at time 0, okay, this is a box of size 4, and the particles are between 0 to 2, so you have only distribution this side, and here there's nothing, right? And after some time what you see is that there's the gas fills the box, so you get a velocity distribution every time, and it's not okay, so now you see that it's no longer Maxwellian if you look at each cell. Okay, because locally, I mean, you can imagine at right in the beginning there's nothing in the right half, but the fastest particles will move into the right half, so it will have a velocity distribution which is not really Maxwellian, right? Okay, so this is at time 8, but at time 16 what you see is that it's almost now Maxwellian, and then again at some time you see there's some structure develops and so on. Okay, and so you see this funny sort of periodicity in the distribution with time, which sort of corresponds to what these oscillations that we see. Okay, how much time? I took 25 minutes.
I have about 12 minutes.
12, okay, thanks. Okay, so okay, so I just want to say that this time here 16 corresponds to this peak here, and then this time 32 corresponds to the second peak in this entropy curve, and this times in between are the ones where you have a dip in the entropy. Okay, so you have a dip in the entropy because there's some structure is developing, while at I mean at this other times it's in some sense more homogeneous. Okay, so this we can understand why this is happening. So basically the period of this oscillation is given by 2L divided by the grid size delta V. Okay, so basically it's like if you have a circle of size 2L, then if you have two particles which are starting with velocity which is delta V different, then you ask how long will it take for them to catch up with each other. Okay, so that time is 2L by delta V, and that corresponds to the time it takes for this winding that we saw in this phase diagram to actually for one winding. Okay, so that's why every time there's a full winding in phase space, I mean in some system, in some sense the system becomes homogeneous, and so you see the peaks in the entropy. Okay, so this is how you can understand these oscillations. And okay, so let me just summarize the main observations for this macro state 1. For any coarse graining, so coarse graining means choosing delta x and delta v. The final change in entropy is always log 2, but as the coarse graining box size is decreased, when we decrease delta v, we see that the entropy growth rate is decreased, and it takes a longer time to reach the saturation value. Okay, this function in the large n limit and in the delta v going to limit, one can show that this function actually satisfies this simple Boltzmann equation with no collision terms, and therefore it makes sense that in this limit there is no increase in entropy. Okay, but so if you really take the thermodynamic limit n infinity and delta v going to 0, then there is no entropy production. But for any in this non-interacting system, but if you really have any finite coarse graining, then you always see entropy production. Okay, and this like I said, for different delta v you get these different curves, which you can actually scale them by using the periodicity, so they all fall on top of each other, and we can compute these curves and so on, which is I won't describe how one can obtain this. Okay, so these are given in the paper, so I won't discuss the scaling function and so on, which we can completely compute analytically. Okay, any questions? Yeah.
So the grid sizes of dividing the total box, does that affect the oscillatory behavior at all, or?
Yeah, the grid size, that's what I said. So okay, so when you change grid size, like in this case change delta v,
right,
what you see is that, okay, so see the saturation comes later, and
but it still saturates to the same value.
It will always saturate to the same value,
right,
only the time scale
only
changes.
the time scale is
right,
coming
yeah,
different.
yeah. So the time scale is this 2L by delta v, right? So delta v smaller, it's a
right,
longer time scale. The period changes and the
right
time scale.
And so in a given grid size,
yeah,
now you have this different deviations from Maxwell distribution, right? So while this deviation is happening, the particles are then undergoing different kinds of displacements per unit time. Is that a physical way to understand it, or like during the time evolution,
yeah,
the particles are undergoing different levels of displacement in a given unit time, like different mean free paths throughout the motion? Is that one way to understand it?
No, see, there's no mean free path. Mean free path is infinite, right? Because they're not completely non-interacting.
Right, but so in a displacement point of view, like throughout its motion, like in given unit intervals of time.
See, right, I mean, in the beginning you can see that, see what happens in the beginning here. So you are asking about this plot, right?
Yes, based on this plot.
Yeah.
In a given unit interval of time,
yeah,
say 1 unit of time or 2 units of time, at the beginning it covers some separation,
yeah,
from one point to point B, and then in an intermediate state, in the same unit of time difference, it covers a significantly different distance, or is that completely uncorrelated?
Okay, I'm not sure I understand. Maybe we can discuss later,
sure,
right?
Sure.
Okay, so now I'll discuss the second macro state that that I mentioned, where you just divide this this box into cells of size L, and then you just ask what is the number of particles in this cell, what is the total momentum and energy for different cells which are centered around this point, different positions x. So this is the usual hydrodynamic description of a fluid. Yeah, so we can then define this density energy density, momentum density fields. And in this case, if you ask again, do this counting, what you'll find is that the entropy is just given by the size of the cell into the thermodynamic, usual thermodynamic entropy in each cell. Okay, so for each cell, since you know the number of particles, their momentum and energy, we know from usual thermodynamics how to compute the number of microstates, right? So we don't care whether the system is in equilibrium or not. This is just a counting strategy. Okay, so to count, you can use the equilibrium formula. So we can use, so this S is now just the equilibrium entropy. Even though the full system is not equilibrium, each cell I can use this counting thing. Okay, so this does not even require local equilibrium or anything. It's just a counting strategy. Thanks. Okay, so this is the equilibrium entropy of an ideal gas, and I can compute for each microstate. I can compute what is the total entropy. And then if I okay, so these are the evolution of the fields, of these three fields with time. So maybe I won't discuss. Okay, so this is just to show that if I take a single realization but large number of particles, they show the same behavior as if I do an average over many realizations with the same initial macro state. Okay, so with increasing number of particles, these oscillations just go down, and you'll get something which is independent, which is the same as if you did an average. Okay, now for the entropy in this case, what we find is that again it has this log2 increase, but in this case it does not. Now I can again decrease my this coarse graining size delta x or L. And here one finds that you get a convergence quickly to some size independent value, and the entropy just has this nice profile. Okay. Okay, so in this case it's monotonic and there are no oscillations. Okay, so this is very different, even though the initial and final values of entropy are exactly the same as for the other macro state. Okay, so this maybe I won't discuss much. If you do in different initial conditions, for example, this is initial conditions where the particles are not chosen from Maxwell but from just each particle has plus or minus 1 velocity. Okay, so in that case the entropies never reach equilibrium. But if we put the slightest amount of noise to this, like if you take 1 plus minus epsilon, where epsilon is some random number, then immediately you get again same situation. Okay, so the entropy again reaches the equilibrium. Okay, so let me go to now the case of interacting systems in the last 5 minutes. So this same system you can make it interacting by considering a gas where the alternate particles have different masses. Okay, so this is light, heavy, light, heavy, light, heavy, and this system and they don't cross each other, they just undergo elastic collisions which conserve energy and momentum. So this system is known to have good ergodicity and mixing properties, and in this case now you see that the evolution in phase space is completely different. You don't get these stripes and so on. This has lots of interesting properties which I won't discuss, and for some time actually you can describe the evolution of these fields exactly by the Euler equations or of hydrodynamics. Now in this case again we can look at the same two entropy functions, and what we find quite remarkably is that both these definitions of entropy lead to the same, I mean they agree completely with each other. So this of course is true in the large n and some limits which have to be taken carefully. Okay, so in this case as you decrease delta V, we don't have this funny dependence on coarse graining for S, the first macro state, and both of them are just increasing functions of time. Okay, so we can also verify that this system is in local equilibrium at all times, and right, yeah. So let me go now. Okay, so the difference in this case is that if you look at the Boltzmann's this equation satisfied by f, this function f in this limit, then it satisfies the Boltzmann equation with a collision term. And so in this case, entropy can evolve, okay? And this is usually what is essentially Boltzmann's H theorem. And what we are giving is a very explicit demonstration of this in a simple system, okay? And this fields, evolution of the fields also we can write an equation where it's Euler equations plus some Navier-Stokes corrections. Okay, so so recently we are also doing this for a quantum case where it's now you can ask how do you do the analog thing in quantum systems. So there you start with a many body wave function. Pavan, I have 1 minute.
Yeah.
Okay. Okay, so there instead of x we have a many body wave function. Which we initially again choose from some thermal distribution, like it's a grand canonical distribution. We just choose one state out of this grand canonical distribution and then study how it evolves with time, right? And then we can again consider the same two macro states as we studied in the classical case, and we can do this counting and so on. Now, for the construction of f of this phase space distribution function single, this is a bit tricky in quantum systems because you can't really ask how many particles are there in each cell. So what we found is that okay, so one sort of usual standard thing to do is the sort of close analog of f is the Wigner distribution, but it is not positive definite and it's not a distribution really. So what we do is we find that you can sort of coarse grain this Wigner function and construct an object which is sort of tells us the number of which basically has the interpretation of the occupancy of some single particle basis states which are localized in both space and time, okay? So this localization is of course up to some h cross limit, but so this is some nice construction that we can do, and using this construction we can now again look at exactly what we did in the classical case, and we find very similar behavior. We see equilibration at some time scale. There is a funny thing that because it's a system which has sort of integer quantum numbers, so there's an exact recurrence. So if you start from a half filled box, after this amount of time it again comes back to exactly half filled, okay, whatever initial condition you start from, but there's you have to look at the limit where you look at time scales much before that, and there's a limit where the system actually equilibrates, and then you can talk of all these things. So there are some other interesting things that the change in entropy is not log 2. For fermions it is between log 2 and 2 log 2, and for bosons it's always less than log 2, okay. Okay, so I'll just summarize. I mean, so basically what I talked about is a demonstration of increase of Boltzmann's entropy during free expansion of an ideal gas. In the non-interacting case, I talked of two possible choices of macro variables, and both show thermalization in some sense, that at least what you are observing will seem to thermalize, and the final change of entropy is log 2 in both cases, with some differences, okay. So I mean, one point is that things like ergodicity, chaos and non-integrity are not so relevant for observing irreversibility. This is one point that we want to emphasize. And what is most important is typicality of initial conditions and large numbers and coarse graining, right? And entropy increase comes because of our lack of knowledge, of detailed knowledge of a system, and that's what is important. Then I talked about the interacting gas, and there we showed that because of mixing and local equilibrium, it ensures that these two entropies, macro state definitions, give exactly the same entropy at all times. Okay, so these are the references. Thanks.
In page number 12, you had 12 or 13 actually. There was a picture where you showed. This is the one actually. I mean, these types that you get actually after a while. is it because of the initial conditions that you take for your configuration to start with?
For any initial condition, and at least if it's in this left half and you start with any velocity.
And then why this pattern appears actually? There is no particles with certain velocities between, let's say, 0.2
that's
to
because it's a non-interacting system and there's no mixing in the velocity. So the velocities are strictly preserved.
Yeah, but why there is a gap actually? That means you are not allowing certain particles having velocities between this.
No, see, I mean, they're not parallel actually. There's a slight slope.
Right.
Okay, so I mean, if you look at any velocity, of course, has to be present, right? Initially, there's all the velocities are present, and here also all velocities are present, but they are just located at different spatial points. But if you, I mean, whatever velocities.
How do I understand this? These stripes actually.
Right. Yeah.
How do you understand it? If there is no dynamics, why it chooses this particular one actually? Why not this wavy or something? Is there any, if I don't have any interaction between them?
See, I mean, the stripes, if you just take this small cell, okay, so what the particles will do here, okay, so they get reflected on, they all start with negative velocities. This is a wall. They get reflected and then they emerge from with positive velocities, right? And they are moving, see this minus 0.5 will get reflected to 0.5 and it moves here, okay. And then it just stretches, right? Because I mean, this guy at 0 won't do anything. It can just only stretch. And now when it hits the other wall, it will just emerge from this side. Okay. So you can see that there can, I mean, because this guy, there can be no spreading of the velocities. Okay. If it was an interacting system, it would spread. This is what you see in the interacting system. But here, because there's no spreading, you will be left with these gaps.
Yeah. Quick question.
So the previous slide, 13th slide. So you show that you starting from certain initial condition and the particular distributing, and you have a linear growth of entanglement entropy. So in the quantum case, there are ways to evade that. That is the localization you said. Is there any classical analog, like instead of free gas, if we take a disorder potential, like some potential very small, so will we have localization in place of like the classical thing? That means different way of growth of entanglement entropy.
Okay, no, see, this is not entanglement entropy. Like Boltzmann's entropy is completely different from entanglement entropy.
Okay.
So, and I said localization, but it's not localization like Anderson localization. This is just, I said you construct wave packets which are localized in space and time for a completely non-interacting system. Okay, so I mean, it's nothing to do with Anderson localization.
So
if you put disorder, I mean, the situation will be very different, of course. Yeah, that will be, I mean, I don't know, because of course their thermalization is difficult and so on. In classical systems, you still have thermalization, I mean, but quantum it will be very different.